Hi, everyone. So I'm re-recording a lecture because I was cut off in the middle of it due to connection issues that I had. So here's hoping that I get through this entire lecture without having any big issues. Um, I hope you're all doing well and that everything's going smoothly despite all of the issues. I know that not everyone was anticipating that they would be spending their remainder of the spring semester this way. Well, assuming that it's a remainder of the spring semester, who knows, things might be a little different. Hopefully what you see in front of you is a collection of slides and from my Prezi slides. And so this is the first set of slides that we're going to use covering inductive logic. And so what I'm going to do is I'm going to give you kind of an overview of what I went over at 10:30 today. Um, and as well as some of the exercises that we covered, which I'll have to pull up. So forgive the clumsy opening of the document as I move through things. Let's take a brief pause and do some thinking back to the material that we covered before I left, before we had spring break. We covered deductive logic, right? And so in deductive logic, what we were concerned with respect to the assessment of arguments was with looking at whether arguments are valid and chiefly with whether arguments are sound. And so we had a few different methods for testing validity. One of the things we looked at was using Euler diagrams, right? You remember those circular diagrams that we had that we use as a way of trying to represent the validity and invalidity of arguments. We also used counterexamples, which were supposed to show that the premises and conclusion can in fact come apart. Well, we also talked a little bit when we were talking about informal fallacies about inductive arguments and the different features of inductive arguments, the ways in which they differ importantly from deductive arguments. One of the things to remember is that deductive arguments are either valid or sound, right? Deductive arguments are valid in that if the premises are true, then the conclusion must be true. That is, a good deductive argument is valid. Not every deductive argument is valid. Some deductive arguments will fail to be valid. But the basic idea is that in a deductive argument, the premises guarantee, as long as the argument's valid, the truth of the conclusion on the assumption that the premises are true. When we have a sound argument, we get the assurance that, in fact, those premises are true, and so the conclusion must be true without any doubt. And so, okay, inductive arguments have slightly different features to them. We're going to focus primarily on strength, and we're going to focus on cogency. And so an argument is strong in the situation where the conclusion is probable if we assume that the premises are true, right? This is sort of like validity. Notice that validity has a hypothetical kind of character to it. The basic idea ends up being that, that it's if the premises are true that the conclusion must be true. We have no assurance that the premises are in fact true. In an inductive argument, what we have is, again, for strength, no assurance that the premises are true, but just this connection between the premises and the conclusion, such that if the premises are true, then the conclusion is probably true. Cogency looks a lot like soundness. Soundness, recall, says that the argument in question is valid and its premises are true, but validity doesn't apply to inductive arguments. And so what we really are going to focus on for cogency is strength. A cogent argument is one that is strong and that has true premises, so that it's very probably the case that the conclusion is true given what we know about the premises. So when it comes to assessing inductive arguments, what we're going to do is focus largely on those features, in particular strength, because strength is going to be the relationship that we're going to be most focused on in the way that we were most focused on validity when it came to deductive arguments. So why care about induction? Well, I mean, the nice thing about deductive arguments is that if you give a good deductive argument, then you just prove your conclusion. You get your conclusion for free after you get true premises. But it's not really if you look around at most of the arguments we give, many of the arguments that are given in different contexts, it actually looks like a lot of them are inductive. They're not deductive arguments. And there are a number of cases we can draw on. I want to focus on two particular cases. One is the case of science. A lot of us think of science as sort of like objective and that the claims it comes to are just true. But the process of doing science is actually deeply inductive, and importantly so, I think, because when it comes to a deductive argument, you really don't get any more information out of a deductive argument than what you have already in the premises. In an inductive argument, you're usually trying to expand beyond the premises to sort of extrapolate to things about the world. And so something like that is what you're going to see as a characteristic feature of a lot of inductive arguments. So let's take one way of modeling the way science might be inductive, just so you kind of get a sense for why it is that someone might think that it is inductive. Some of you have probably been taught in your basic science text that there's this process, this procedure for doing science, where the idea is that you kind of formulate a hypothesis, and then after you formulate your hypothesis, you try to design experiments that test what implications are of the hypothesis. So we look for things in the world, or we set up experiments that allow us to see certain things, so that we can then infer that the hypothesis is true. And if you try to set that out in kind of a systematic way, it doesn't look like you end up with a valid deductive argument. So for example, if we assume that a hypothesis is true, then we might say that we should expect certain observations to occur, right? If we assume that the Earth revolves around the sun, then we should be able to make certain observations about the movement of the sun relative to the Earth. And then let's in turn say that we do in fact make that observation. Then we might infer that H is true, or that H is mostly correct. We might want to perform further tests using H, but supposedly getting the observation that's implied by the hypothesis would suggest to us that we are in fact on the way to truth. But now, if you pay attention to the structure of that argument, and you consider the way I've set it out here, this should look to you like a formal fallacy. It should look like an instance of affirming the consequent, which, if you recall, is invalid. We can construct counterexamples to affirming the consequent. And so this suggests that we can't use validity as a criteria by which to assess this process of doing science. In fact, we need to turn instead to strength. Maybe the observation lends a certain degree of support to the hypothesis, and so because we make certain observations that are implied by our hypotheses, the probability of the hypothesis goes up or down depending. You'll see more on this later when we get to later portions of the course. But the idea here then is that science, in as much as it relies on this process of formulating and testing hypotheses, must be inductive. So a lot of the scientific arguments that we may have access to are going to be inductive arguments, right? Why do we think that things like social distancing work as a method for controlling viral spread? Because presumably we've seen it in other cases. There may be some mathematical reasons about exponential growth and things like that that we can draw on in the background, but the idea is that because it's worked in the past, we might be able to say that in fact it will continue to work into the future, and that starts to look a little bit like an inductive argument. Another case where we find inductive arguments is in the case of testimony in the law. So a lot of court cases, for example, would rely on witness or expert testimony to try to construct inferences and say like, well, in fact, we have reason to believe this and that this person broke this law for this reason because they were seen doing this on this day or whatever. But if you try to break down the structure of an argument that bases itself on testimony, you should be able to see straight away that this is not a valid argument. One thing for sure is that the argument just says that because someone says that something is true, that therefore it must be true. Well, obviously that's not the case, right? There are lots of people who say lots of things, and it could very well be the case that somebody is saying something that's false. They could be an unreliable authority about a certain matter. We've talked about that when we talked about informal fallacies, right? That it's possible that somebody might be an unqualified authority, and so we shouldn't take their saying something as evidence for the conclusion that it's true. But in law, we require we oftentimes appeal to these kinds of sources, and in everyday life. You're listening to this lecture right now, you're taking it to be the case that if Richard says a certain thing about logic, then, or at least basic reasoning, then it must be true, right? I'm not going to lead you astray. There's an implicit argument happening there. You're thinking about me as an authority, and you're thinking that I'm a reliable source, but I'm human. I could make mistakes. And so the fact that I say something doesn't necessarily mean that it's true, but it could mean that it's very probably true. And so in this case where we, like, not only in the law, but in everyday life where we rely on what others say to be able to do anything at all, well, we're relying on testimony and therefore relying on induction. So what we're going to do then is take stock of a bunch of different inductive argument forms and try to show you the different patterns and different ways in which induction typically happens. And we're going to go over some general strategies that you can pursue for evaluating and assessing inductive arguments. So next slide. So we have a bunch of different argument forms here. Earlier, when I tried to record this, I only went over statistical syllogism and inductive generalization. And so that's what we're going to do today. After that, I'll go over a few exercises with you that help to convey some of the skills that you want to generate. I'll answer a few of the exercises, and then I'll leave you to use the rest to practice. All right, so the first general argument form that we're going to talk about is what's called statistical syllogism. It has this general form. Most A's are B's, X is an A, therefore probably X is a B. Which you can contrast with a deductive form, which says all A's are B's, X is an A, therefore X is a B. In this case, there's one clear difference between these two arguments, and it comes into the first premise. Technically, there's a difference in the conclusion too, with the word probably, but one of the most important differences is between the use of most and all. So think about how you would diagram, think about an Euler diagram for the second argument on the right. You would have the big category B, you'd have the smaller category A inside of B, and then you would probably say that, hey, there's an X inside of A, and so since everything in A counts as a part of B, then we may conclude that X is a B. Well, most here is going to show that, in fact, we can only ever say that it's probably the case on the assumption that those premises are true. Consider again, take the big category B, take A. Now, because most A's are B's, but not all A's are B's, the way you might try to draw that is to push the A circle outside of B a little bit. Make sure most of A is still in B, but a little bit of A can fall outside of B. And so when we say, well, X is an A, well, then we might conclude that, in fact, probably it is a B because most of the things that are in A are in B already. So this suggests that it's possible for those premises to be true and the conclusion false. But it could be, and so that's always going to be the case with an inductive argument. But the idea here is just that, right? That you can securely infer that something is probably the case given what we know about the information in the background. That is, that most A's are B's and X is an A. Okay, so we'll go over some exercises with this in a little bit, but let's go over some of the general features of this argument. So here's an example of this argument and the way it might work. We have this example: most musicians can read music. Sheila is a musician, therefore Sheila can read music. We're going to break down statistical syllogisms into a number of components. One thing is that we have different categories and different populations that we're talking about. And with those different categories and populations, we have an individual that is participating in multiple populations. So for example, Sheila is that individual. She's a person, right? Sheila, we're saying in this argument, is a musician. We're also saying that musicians are people who can read music. And on the basis of those two pieces of information, we're inferring that Sheila can read music. So in that second premise, that Sheila is a musician, what we're doing is we're introducing Sheila into a reference class. We're assigning to her the class of being a musician. And in turn, to perform the function of inferring from those two premises that she can read music, we're using that reference class as a way of attributing to her an attribute class. It's the class she belongs to because she belongs to the reference class. So in this argument then, musician is a reference class. Being a person who can read music is the attribute class. Okay, so I'm going to take a step back. And to assess this argument, we're going to need to consider one of the major strategies for dealing with inductive arguments. Okay. So to assess an inductive argument, what we're going to do is we're going to look for defeaters to the argument. Okay, so defeaters to the argument are going to be reasons we have either for believing that the conclusion of the argument is false, or for believing that the argument really supports the conclusion well in the first place. Okay, so a deductive argument, for example, like just to sort of contrast, a deductive argument is one that we try to assess by looking at its soundness. We consider whether the premises are true or whether it's valid, and we either try to show that it's invalid or we try to show that one of its premises is false. We can't do that here. For inductive arguments, what we're going to do is look for defeaters. Okay, so a defeater, we have two kinds. We have undercutting defeaters and we have rebutting defeaters. An undercutting defeater shows that the premises only support the conclusion weakly. There is a possible situation where the premises become separated or severed from the conclusion. Rebutting defeaters show that the conclusion is false, despite whatever support might be yielded by the premises. So the idea here then is that we're going to pay attention to certain structural features of inductive arguments. What we want to do is we want to be able to show that there's information we can introduce to the argument that affects the inference being performed. Okay, so what we're doing here is we're going to imagine situations related to the ones described in the argument where the inference from the premises to the conclusion will be affected. For undercutting defeaters, we want to think about what information we can add that will impact whether the argument comes out, whether the conclusion is really strongly supported. I'll give you a concrete example of that in a moment with the Sheila example. To find rebutting defeaters, we need to think about situations where the premises could turn out to be true, but where the conclusion would still turn out to be false. This isn't the same as testing arguments for validity. What we're here trying to show is that it's not the case that the conclusion is probably true because there's some reason to believe that the conclusion is false in the first place. So this is just elaborating on that last point. You can take a look at this on your own time in the Prezi slides. Let's return to assessing statistical syllogisms. So the main principle that we're going to deploy for assessing statistical syllogisms is to consider what's called the principle of total evidence. The principle of total evidence simply says that we should make use of all of the evidence that we have available to us. Okay? So doesn't mean that you need to go out and find all of the evidence for any single subject matter. You know, in this case, because we don't have the time for that in class, what we're going to do is instead think about the shared information that we might have in common that we can use to assess the relationship between the premises and the conclusion. We're going to use our common ground, background information that we might be able to deploy to test the strength of an argument. So let's go ahead and take a look at this example. Again, the argument says most musicians can read music. Sheila's a musician, therefore Sheila can read music. We want to imagine situations that might help give us either potential rebutting defeaters or potential undercutting defeaters. Here's an example of a potential rebutting defeater. Let's suppose that we learn that Sheila is blind. This would show that the conclusion is false. Then note, this means that we're reading read in a very specific way. The word read here is being understood as sort of involving some kind of visual stimulus and, you know, cognitive processing that's associated with reading as we normally think of it. She could, you know, read Braille, obviously, without having vision. But in this case, we're going to assume that read means having that visual stimulus and that cognitive processing associated with it. And so we learn that she's blind. And if she's blind, and if we assume that music is not going to be read in Braille or anything like that, then we would be able to say that it is in fact false that she can read music. Okay, so that would be the rebutting defeater. So it might, but notice that it's still true that most musicians can read music, maybe every other one other than Sheila can, and that Sheila's a musician. We could assume that as well. She could just be a blind musician. And so, but then the conclusion that she can read music comes out to be false once we introduce that piece of information into our shared background knowledge, right? So this is the kind of information that if we learned would serve to undermine the inference to the conclusion by showing that the conclusion is false. All right, so now for the potential undercutting defeater. So for the potential undercutting defeater, what we can do is we can start to imagine about the different ways we can divide the population even further. So Sheila's a musician. That's the reference class to which she belongs. But are there any other smaller classes to which she belongs that might be subject to different rules than the ones that every other musician are subject to? Let's suppose, for example, that Sheila's an avant-garde musician, somebody who, for example, might value just improvisational music, right? They don't think they should be bound to notes on a page. Instead, they're perfectly comfortable with the idea that they should be able to improvise everything, and so don't require sheet music to perform their work. And so some avant-garde musicians may not engage in the act of reading music at all. Suppose we learn that Sheila's an avant-garde musician. If we do, if she is in fact an avant-garde musician, then while it might be all three of these things might be true, the first two premises don't necessarily show it, because Sheila's status as an avant-garde musician makes it less probable that she's somebody who can read music, because, well, avant-garde musicians don't necessarily have to be able to read music. So there you have it. You have a potential undercutting defeater. Now notice we're not saying this stuff is really true in this case. If you were to go in and try to show really that some inductive argument is uncogent by formulating defeaters to the argument, then what you would have to be able to do is show that in fact the information you're drawing on is true, that it's correct information, that it's additional information about the individual and the population they belong to that really undercuts the argument. Here, I'm trying to get you to formulate strategies that can help you to address the cogency of the argument. So how would I have to go about, what information would I have to find if I wanted to be able to show that the argument is uncogent, all right, or weak? So there you have it. All right, so just to sort of stress the difference then. Rebutting defeaters add information that shows that the conclusion is false, that the premises are true. This is to say that the conclusion isn't probably true. The premises might be true, but that conclusion is not true given what we know about the individual that the argument is talking about. Undercutting defeater adds information that shows the conclusion is less probable given the premises. So though the conclusion is not demonstrated to be false, right? It could still be the case that Sheila reads music. It's just that the premises, now that we know that Sheila's an avant-garde musician, don't really lend as much support to the conclusion as we would have initially thought. All right, so that's a statistical syllogism. Let's turn to what's called inductive generalization. So inductive generalization, I want to focus on it because it's importantly different from statistical syllogism. Inductive generalization moves from a sample population and then tries to infer something or extrapolate something about the population that sample belongs to. Now, under normal conditions, this can be a perfectly reasonable way to draw an inference. It's not a huge, it's like many of you have probably had a statistics course, and in those courses you learn things about representative samples and sample sizes that are important from the standpoint of being able to say things about the population by drawing on a sample. People who do political polling for electoral campaigns are oftentimes in the same game of trying to infer strongly certain conclusions about the population and their voting behavior on the basis of samples. Rarely do any of us have time to go through and really collect information from every single voting American to determine exactly how they're going to vote. So usually a sufficiently large and representative sample is used as a surrogate for claims about how the entire population is going to vote, right? So last time we encountered this argument pattern, and this is why I'm stressing this point, is in the context of what we call the hasty generalization, right? So a really simple version of a hasty generalization might look like the argument on the right here. There's one sock in my drawer and it's black, therefore all socks are black. Right? Without knowing enough about my drawer, we might say that in fact that's a little too quick. We need some additional information about the contents of my drawer before we can say anything about the contents of every sock in my drawer. And so this is where defeaters for inductive generalizations come in. So we want to be able to either find undercutting or rebutting defeaters for inductive generalizations. And this is going to differ a bit from what we saw with statistical generalizations. So statistical generalizations, recall, you add some information about the individual, you add some information, or you add some to either falsify the conclusion or to show that the conclusion is only supported weakly by the premises. Undercutting defeaters for inductive generalizations and rebutting defeaters look a little bit different. What we're going to do is look at the ways in which the sample might be influenced wrongly in ways that negatively affect the conclusion, show the conclusion's false, or show that, in fact, the conclusion is not going to be very well supported by the premises. So let's go back to the sock example. The sock example says that there's exactly one sock in my drawer and it's black. I'm sorry, there's one sock in my drawer and it's black, therefore all socks in my drawer are black, right? So we say there's at least one sock because there may be more. I want to make sure that's clear. But let's think about what the potential rebutting and undercutting defeaters would be, right? Let's suppose that you learn that there are no other black socks in my drawer, right? Well, okay. In that case, if there are no other black socks in my drawer and there are socks of every other color, then we would have an undercutting defeat, or sorry, we would have a rebutting defeater that shows that in fact not all socks in my drawer are black because there are no other black socks. That's the one black sock. It had no friend. It was there by itself. I happened to take it out and it's gone. Now let's suppose instead that there might be, we'll have to qualify that for the purposes of this discussion, other than the way it appears on the slides, there might be a red sock in my drawer. That is, I went to the store yesterday and I bought a pack of multicolored socks, and I think I remembered to put them in the drawer, but I can't remember if I did. So there's definitely some plausibility to the claim that all socks in my drawer are black. That is, it's not just straight out false in light of the premises, and this information about the socks I bought doesn't immediately show that that conclusion is false. But this question about whether those socks made their way into my drawer and that I have those socks in my possession, and whether I have those socks in my possession, does something to show that the conclusion might be less likely to be true in light of that piece of evidence, right? And so that's the way you might find an undercutting defeater. So notice what we're doing here is, we're just sort of searching for the kinds of information that we would need to be able to show that the premise is in fact not directly determined, doesn't directly determine the conclusion in the way needed for an inductive argument to be strong. So that's the way this might work. And there are three kinds of biases that might affect arguments in this way. In the last example kind of drew on one of these biases, but let's take a quick look at each of them so that you get a feel for what's going on here. So the first one we'll talk about is the selection bias, right? So the question of a selection bias is just how the sample from the larger population was selected, right? In the sock case, I just drew a random sock and just said, oh, look, I drew this color sock, so every sock must be the same. In which case, there might be something about the way I drew that sample, given the number of socks in my drawer, that is incorrect. I need to make sure that I pay attention to certain features of the sample that I drew, like, for example, sample size, and not just the size of the sample, but also whether the sample is sufficiently representative, right? That's the main question here driving selection bias, is how the individuals in the population were selected for their use in the argument. Okay, so that's selection bias. The next two biases are sort of bound up in what we might think of as survey responses. So thinking about how surveys work in like, especially surveys that go around, like people might call you and try to poll you about your attitudes about certain political issues and things like that. And you know, there are different ways in which those kinds of arguments that draw on that kind of data can be problematic. And so, for example, we might think about what's called the response bias. And in this case, the idea is that the sample ends up being kind of polluted or distorted because the procedure we take for drawing on the sample is one that makes it so that only certain things are likely to be a part of that sample. And so in this case, the idea here is that being likely to respond might be problematic. So for example, there's this famous situation from the 1936 presidential election where people were collecting information about different presidential candidates and then looked at, and pollsters started using phones. The problem is that the phones were relatively new technology at the time, and so only certain groups of people really had access to phones, and those people typically had certain political biases. And so the judgments that they formulated about who would win the election in the 1936 election might have been, or were, incorrect on the basis of who they were able to get to respond, right? So, you know, going on to Fox News and looking at an opinion poll about whether Trump is doing an excellent job, is if that poll is only collected from, say, like readers on Fox News's website, well, people who are likely to be in support of Trump would likely be the ones responding to that survey. And so extrapolating too much from that survey might be problematic. And noting where the survey comes from might be the basis for formulating a defeater against the inductive generalization. Similarly, there's what we call the non-response bias. The non-response bias rests on the opposite problem, which is just that sometimes people fail to respond to certain things, and so you might end up with a distorted sample on that basis. So going back to the example of the 1936 election, people were called on their phones, but of the 10 million people called, only 2.5 million responded. And so you might worry that those remaining several million people, the 7.5 million people, might sway the opinions or our judgments about the prevailing opinion in very specific ways. So that if we learn that additional information, then any kind of projection we try to come up with, say in the case of trying to predict who's going to win a presidential election, may not work out in the way that we want it to. That is, we may not get to a conclusion that's probably true about future voting behavior, right? And so a non-response bias can influence things negatively as well. Okay, so that's where we're going to stop, at least on the slides. I'm now going to take a few minutes to open up a document and give you a little survey of some of the questions that we're going to be looking at, and for the first set of worksheets. Okay, all right, there it is. My apologies. This is definitely not getting re-recorded though. Okay, here it is. So we have 3 sets of exercises here. These are mostly about statistical syllogism. The first set says, for each of the following, identify whether the argument is a statistical syllogism or not. Do this by trying to make it fit into the argument that describes statistical syllogism. So one thing I'll have you do is just kind of go through, and one thing you could do is just write down what the argument form is. Sorry, guys. Tech has given me all kinds of trouble today. All right, maybe this will fix it. All right, so there we go. So this is the general form of a statistical syllogism, right? Zoom in a bit. The question is, whether this, how we can fit the information here into this general structure, and whether that's the way, whether it in fact has that structure. So let's look at this. It says most students pass this class. Since you're staying in, you'll probably pass. And you know, this seems like it's a pretty straightforward one. You are an individual and you belong to a particular group, namely students in this class. And then there's an attribute that you're receiving in the conclusion, which is that you're going to be a student who passes this class, or probably you're going to be a student who passes this class. And so the way you might fill that in then is to just say, well, okay, most students in this class are students who pass this class. And, well, you are a student in this class. Therefore, probably you will pass this class, right? So, but notice that before I could fit it to this structure, what I really need to be able to take note of is just that the information that information in the original argument actually matches the information that's in the premises. So here it's pretty clear. There's a use of most. There's this probably. There seems to be an individual involved, namely, I guess, whoever you is. In this case, it might be me. And in that case, what we have is something like, what we have is something that seems to be pretty clear-cut statistical syllogism. And so you should notice that squeezing it into this form, the structure that I had a moment ago, actually seems to preserve the content of the argument, right? This number 2, for example, is a little less straightforward. Few students come to class on Friday morning. Sasha probably won't be there. So in this case, you know, like the most is gone, but there are other cues to look out for. So we have few students, right? And we have probably, and this seems to be leading into a conclusion. And in that case, then that suggests that possibly what we're dealing with here is a statistical syllogism. The question is, are all of the other elements there? So let's say we have most students in this class are students who do not come to class on Friday morning, right? That would definitely be the premise, one of the first premises. The next premise might be something like this. Sasha is a student in this class. Therefore, Sasha will not come to class Friday morning. Probably. There should be a probably here. So in this case, it looks like by squeezing it in, we preserve the relevant information. There's an individual who's a part of a reference class, and then that individual is being assigned a particular attribute class on the basis of their belonging to that reference class. And so we have what seem to be all the relevant elements that we need to be able to say that, in fact, this is a statistical syllogism. Let's contrast that with the next one. So we have many pundits agree that prison reform is necessary. Therefore, it's probably true that prison reform is necessary. Now notice here, we do seem to have the elements of an inductive argument, okay? It's probably true. That's the inference to the conclusion is only probably, right? The premise seems to say something about what it is that many pundits believe. If you think back a moment ago to what we were just talking about with testimonial knowledge, this looks like we're making an appeal to authority, that because the pundits agree that prison reform is necessary, then we should also believe that prison reform is necessary. So it might look something like this. So this is either just a pure testimonial claim or a claim about what we should believe, right? So this also seems pretty plausible as a way of characterizing the reasoning. And this is not quite an inductive generalization, but it feels very similar. And so you might think that this is another way of reconstructing the reasoning. But either way, in this case, notice that we don't have an individual, and we don't have, and so we don't have that reference class the individual is being slotted into, and we don't have the attribute class that they're being slotted into. There's literally no reference to anything that has membership in some class, and no corresponding inference to the conclusion that that thing also belongs to some further class because of its membership to the attribute class. And so in this case, this is not going to be best set up as a statistical generalization. It's either going to be an argument that relies on some appeal to authority or testimony, or it's going to be something that looks a little bit like an inductive generalization. But I think the best fit's probably going to be the case of, it's probably going to be the testimonial argument or the appeal to authority. So that's how you would take care of those. I encourage you to sit down with the form, the structure of the argument, and fill in the variables and see if what you get makes sense given the structure of the argument. So I'd even go so far as to cut and paste the statistical syllogism and then see if you can fill in the variables in a way that makes sense. So the next set, I'm going to go over one of each for the next ones. So so for this one, for the next exercises, identify the reference and attribute classes, discuss any widely known or plausibly assumed background information that is relevant to the strength of the argument. So in this case, we have most US presidents have been white, so Barack Obama is white, right? This one has a suppressed premise. It looks like an enthemy. And so in this case, the suppressed premise seems to be that Barack Obama is a US president, right? So most US presidents have been white. Barack Obama is a US president, therefore Barack Obama is white. But we know that Barack Obama is not, I guess, under the strictest definition, a purely like white European descended male. In fact, he's considered to be our first African American president. And so in this case, we at least have some reason to believe that there are defeaters to this argument, actual defeaters, not just ones we're kind of entertaining, but real actual defeaters. In this case, there's information we can draw on about, like, say, Barack Obama's parentage, about just, ordinary visual observations of Barack Obama and what we normally think of as sort of like characteristics of white people. And Barack Obama doesn't seem to quite fit with them. And so the conclusion seems to be defeated in a way. It seems to be defeated. And so we can also think about other information that might be relevant here, but those seem to be some of the key considerations. Now, the reference class, well, once we fill in the information, it looks like US presidents is the reference class because Barack Obama is being assigned to that category, right? And then being a white person is the attribute class because in the conclusion, that's the attribute we're saying that Barack Obama possesses because he belongs to the reference class, right? So in this case, then those would be the two, those would be the reference and attribute classes respectively. The reference class is being a US president, the attribute class is being a white person. And I hope that makes sense. That's how I would go about doing that one. Again, you can kind of just like plug in the skeletal form of the argument and then try to fill in all the variables to see how you would need to complete it. And then from there, identify the different pieces of information. You should also practice without the skeletal form because you want to be able to pick up on these things without necessarily having to rely on that skeletal form every time. But after you practice with that skeleton a little bit, you'll probably be able to pick up on those features pretty quickly as you read through some of these examples. So let's use one more example from this first exercise in the third set. The instructions just say, are these enthymematic arguments best construed as deductive or as instances of statistical syllogism? So here you might get both the skeletal forms from the Prezi slides, the inductive form and the deductive form, right? So we have Fritz is selfish, he's a cat after all. And this is saying, well, look, we have reason to believe that Fritz is selfish, namely it's because he's a cat. And so one way to read this is to say, well, all cats are selfish, Fritz is a cat, therefore Fritz is selfish. And notice that the argument here is not hedging at all. It's in fact saying, look, point blank, it's not probably the case that he's selfish, he's just selfish. And he's a cat after all, right? It's sort of like dismissive almost. And so it seems to be saying something about every cat, that all cats are selfish. So if you have to choose between most cats are selfish, Fritz is a cat, therefore Fritz is probably selfish, and then all cats are selfish, Fritz is a cat, therefore Fritz is selfish. At least my inclination is to say that the more natural interpretation of this passage is to treat it as if it's a deductive argument and not as a statistical syllogism. So I wouldn't conclude that this one is a statistical syllogism. But this is what you want to do. Set them side by side. Think about which one you think better conveys the information. Look for things like most, few, many, probably, right? Those kinds of words are usually the cues you want to try to find to see if they'll work. And another thing you might think about is like, well, which is fairer, right? What do people usually mean? Sometimes there's stuff in the background here that's influencing the way we want to set these arguments up. And so thinking about why it might be fairer to go in one direction rather than another, depending on what you're trying to do, right? Depending on whether, if you're trying to criticize the argument, right, then you want the fairest version possible. And so you want to be able to think about what those considerations are that make one particular way of representing the reasoning a fair rendition of that reasoning. Okay, but that's what I'm going to leave you with. And remember that Thursday at 10:30, I will be available to talk to you about your exercises, and you should be able to get as much help as you want. If you need to make a time with me outside of class, outside of the normal scheduled times anyway, to be able to sit down and talk about the exercises, I'm happy to do that with you. But otherwise, just do your best and get in touch with me when you're ready for the quizzes. Okay, all right, thank you.